Are we good?
We're good.
So we finished talking about the sun today. Then lab tomorrow. Has anybody looked at the syllabus?
No.
Lab tomorrow, review Thursday, test Friday.
Test on Friday.
Test on Friday.
What day is Friday?
Viernes. Is that Friday?
I think so.
What day is Friday?
That's the
That's it.
That's the day of Freeze,
Well, I mean, like,
which is one of the gods.
what day?
Well, you can. Today's a 2-day.
Yeah.
3-day, 4-day, 5-day.
It'll be a 5-day on Friday.
Okay, so this is where we left off last time. Are y'all with me? This is a coronal mass ejection. It's a big bunch of material that gets shot out of the sun. And they got this little, this is a special type of telescope where it can create its own eclipse. And what they do is they have this disc that covers up the sun so they can see what's going on around it and not lose everything in the glare. And you can see a big burst of material coming off the sun here. This part, if you're wondering, here and here and here, that's part of the sun's corona. And so what can happen is the magnetic field twisting and churning about inside the sun can throw off a bunch of material. And that material comes floating through space. This is what I was doing at the end. Floating through space, and it eventually can envelop something like the Earth. If the Earth is in the way of this material, there could be problems. Ms. Bradford, what I was talking about when she saw a program that was saying, nowadays with our electrical power grids, if a big coronal mass ejection hit the Earth, it could knock out all our power lines, could blow transformers and stuff. And theoretically, if a big enough one hit, power will be out over the whole planet, which would be a catastrophe. It's bad enough when power goes out just in one place. So, that is kind of scary. The last big coronal mass ejection that hit the Earth, they think was in 1820. A real big one, or 1840 or something like that. And it knocked out a bunch of telegraph lines. Luckily, there wasn't much electricity on the Earth back then.
So they could happen at any time. Just
They can. Mm-hmm. But, it's not at any time. It's usually at times of high sunspot activity. When in the 11-year solar cycle, there's really a lot of magnetism going on. Do y'all remember that it went in 11-year cycles?
Yep.
Did y'all get this right on the quiz?
I did.
High sunspot, low sunspot, high, low, and 11-year cycles. And so you'd likely get a big coronal mass ejection at the peak of one of these cycles, because that's when the magnetic field's really all twisted up and everything. So you wouldn't expect to get one between cycles. Not a big one. So here it shows what this is the coronal mass ejection, this huge bunch of plasma approaching the Earth. And the coronal mass ejection itself is a thing. It's got a bunch of mass. It's got protons and electrons and hydrogen and helium ions, and they're approaching the Earth. And it's got its own magnetic field. See that blue line? That's the magnetic field of the coronal mass ejection. And here's Earth just sitting here minding its own business, just floating around the sun. Y'all are probably right about there, doing your little cheers and stuff. And then the coronal mass ejection hits the Earth, and what happens to the Earth? Well, it messes up our magnetic field. And if the polarity of the coronal mass ejection is reverse of the polarity of our magnetic field, it can kind of cancel out our magnetic field for a short time. And all that stuff can come into the Earth's atmosphere and cause a bunch of problems. There has to be a lot of things lined up just right to get a real bad effect on Earth, but it could happen. You wouldn't feel anything, but it would really screw up the transformers. It would cause electrical surges in any metals, any wiring and such. You want to see video footage of a coronal mass ejection? you want to just say the words coronal mass ejection on 3? 1, 2, 3.
Coronal mass ejection.
Oh, that was beautiful. Did y'all hear that? Okay.
We did. We heard it.
I heard that laugh too, Carol.
Oh, here we go. That's what y'all said.
Young stars in a new star cluster are in constant state of turmoil. Some of them, especially the hot massive stars, can produce flares thousands of times more intense than our sun does today. Here we see one such star launching a huge flare. Such flares could significantly affect life on any nearby planets, one of which is shown here being irradiated in blue light as the flare passes by.
That was pretty bad. The flare is the event that can lead to the coronal mass ejection. Here's what the sun would look like if you look at it with an X-ray telescope. And you see this dark area there that is not emitting a lot of X-ray radiation. But the rest of the sun is emitting some X-ray radiation. And again, these little holes that you see on the sun where we aren't getting much X-ray activity, that's again due to the magnetic field of the sun. The magnetic field just has all kinds of weird effects. I already showed you the video of all these looping electric field lines. That's what the corona looks like at the peak of the activity, of high activity of the magnetic field. I'm sorry. That's what it looks like during low activity, and that's what it looks like during high activity. You see how much more active the corona is, and it's not uniform either. So low activity, high activity, and again, it goes in 11-year cycles.
When the moon covers the sun at a total eclipse, the corona is visible by naked eye. This rarefied outer atmosphere is far hotter than the chromosphere and photosphere below. And it displays magnificent loops of electrified gas. These satellite pictures show the loops curving round magnetic force lines. They can span 30 times the diameter of Earth. A mysterious energy source at their base heats them to 2 million degrees. But solar flares are the most violent convulsions. A single flare can release the energy of 1 billion megatons of TNT. This is one of the most powerful. Here it is again, erupting near a group of sunspots. It triggers a coronal mass ejection, particles hitting a space probe millions of kilometers away. Twists in the magnetic field are the likely cause of flares and their mass ejections. Between these eruptions, the sun emits a steady stream of tenuous gas and electrically charged particles, the solar wind. Normally it blows at up to 400 kilometers a second. But at the time of flares and mass ejections, it becomes a storm. We can't see it, but instruments detect it. The sun throbs in regular 5-minute beats. The cause is sound waves generated by pressure fluctuations deep inside. They provide scientists with an audio picture of the interior. Trapped and bouncing within, the sound waves vibrate the surface in millions of patterns.
Big vibrating suns making all these weird sounds. Crazy. Okay, what's going on inside the sun? Well, here's what scientists think. Of course, you can't get inside the sun and look around. It's too hot. But here's what we guess would happen, and we know a lot of this from our nuclear accelerators, in which we can, on the Earth, accelerate things and make them go real fast and run into each other, which is what we think would be happening on the inside of the sun. On the inside of the sun, there's a ton of gravity, you see, and the gravity's real strong. Now, normally, if you have two protons, which are charged particles, which is what makes up the sun, lots of protons, which is a hydrogen nucleus. Do y'all know a hydrogen nucleus is a single proton with an electron going around it? That's a hydrogen atom. Did y'all learn this in chemistry?
Yeah.
So, imagine a hydrogen nucleus. The electron's been stripped away because it's so hot up there. So much heat. The electrons just will absorb that energy and jump away. So you have naked nucleus. And imagine all these naked nuclei being pulled in by gravity to the middle of the sun. And you start putting all those together real tightly. Now, normally two protons, they wouldn't connect with each other. It's like magnets. Have you ever tried to get two oppositely poled magnets to come together? Ever tried to do that? These magnets are a good example. These are real strong magnets. And if they're oppositely, if you got them turned the wrong way, they're not going to want to come together. Y'all ever play with these rare earth magnets? Pretty incredible. So that goes right together, but if you turn it around the opposite direction, you can't, it doesn't want to go together. It's fun to play with. And then, it turns right around and goes together that way. Cool? Are you getting any of this? Or no? Missed it all? Missed it all? See, the magnets, they don't want to go together that way, but turn it around, they go right together. Yeah? So protons are like this. Protons have the same charge. If it's the same charge, they don't go together. And so you see the protons would come real close together, but would repel each other and go away from one another. But if you get enough gravity and enough pressure and have enough stuff pushing from the outside, you'll eventually push these things together even though they don't want to go together. And that's when the magic happens. Are you with me, Taylor? If two protons get pushed together against their will, they don't want to go together. They normally repel each other. But if you get them together, they'll slam together and make a new nucleus called a deuteron. And that'll give off a bunch of energy. Because if you weigh the deuteron, it weighs less than the two protons combined. You also have to factor in, when they do this type of thing, another particle comes out called a neutrino. And another particle comes out called a positron. These are nuclear reactions. You're changing the atoms themselves. No longer do you have hydrogen. You have this new nucleus, which is called heavy hydrogen. It's a little bit different from these protons by themselves. It's a proton and a neutron together. And a bunch of energy comes out. That's the energy of fusion. Have you ever heard of Einstein's equation? It's called E equals mc squared. Have you all heard of this?
Oh,
Yes.
Now, this is an equation that will measure how much energy comes out of this reaction. If you take the mass of what you started with, which is 2 protons, and you take the mass of what you finished with, the deuteron, the positron, and the neutrino. Well, the deuteron, the positron, and the neutrino weigh less than the 2 protons did. What happened to the extra mass? It was converted to energy by this equation. This is Einstein's famous equation. You take the mass, whatever was lost, you multiply it by the speed of light squared, c is the speed of light, you end up with the energy that comes from this reaction. This reaction gives off a bunch of energy. You can imagine the speed of light squared is a very big number. 300,000 kilometers per second squared. It's going to give you a huge number there. A little mass can make a lot of energy. That's what's happening in all nuclear reactions. In this nuclear bomb right here, a little bit of mass is being converted into energy. And so you get this huge explosion. And that's what's happening in the center of the sun, they think. And so you have all these protons coming together to make deuterons. And this picture shows that even the deuterons can come together with more protons and make something called helium-3. And helium-3 can come together to make something called helium-4. This is what's happening inside the sun. Protons, which are basically hydrogen nuclei, are being converted to helium. Atom by atom, molecule by molecule, you're making helium and losing hydrogen. That's what's going on in the center of the sun. It's been going on for about 4 billion years. And they reckon there's enough hydrogen in the sun where it'll go on for about 4 billion more. It's equivalent to 100 million nuclear bombs per second. That's how much energy is going off in the sun. And it creates all this radiation, and all this energy leaves the core. The core of the sun is where the nuclear reactions are happening. And the radiation leaves, and all the energy leaves, and it takes the energy a long time to eventually get out of the sun. But the only place that nuclear fusion is happening in the sun is in the core. The rest of the sun is just a bunch of hydrogen and helium that is hot because it's near the core. So what is this device? It talks about this in your book. This is a huge device that's made to see if that theory about what's happening in the sun is correct. It is a neutrino detector. Let me back this up a little bit. So if protons and protons are really smacking together, and deuterons and positrons and neutrinos are coming out, we ought to be able to detect the neutrinos. There should be something like 100 trillion of them per millisecond coming out of the sun in every direction. Going through our bodies right now are trillions and trillions of neutrinos, if this theory is correct. And neutrinos are almost impossible to detect because they're very light particles and they're so small. They just go right through everything. If they're real, they'd be going right through me right now.
Are they smaller than an electron?
Smaller than an electron. And much less massive.
Are they impossible to detect if they have a neutrino detector?
They're not impossible to detect. They're just improbable. And they're just hard to detect. To detect them, you have to make something like this, which is a giant neutrino detector that they fill with a special kind of water. This water contains heavy hydrogen as part of the water molecules. And what will happen is, as neutrinos go through this water, every several months, one of the neutrinos should react with a water molecule. It's a special type of water. And when a neutrino hits the water molecule, it should make a little flash of light, if the theory is correct. And so about once every 4 or 5 months, I'm not exactly sure the time period, they get a little flash of light in this huge container. And all those things on the wall of the container there, those are detectors. And they'll detect the flash of light.
So right there, are they like floating in a pool of water?
Yeah, they're floating in the pool of water trying to fix one of the broken detectors.
Oh my gosh. Where is
And
this?
they have these are deep underground.
Oh.
They got to get them away from any other radiation source, so away from radio waves and TV and all that, so they build them deep underground. These huge caves, basically, that they build this neutrino detector in. Here's another one that's seen from the outside. They're down deep in the earth in a big cave, and they've got a neutrino detector, and those are people there, you see? And they're looking at it. They're going, my God, what have we built? It's huge. This is awesome. And so inside that container is a bunch of that heavy water, and neutrinos should go right through the earth, right through the rock, and right through the container, but every once in a while one of them will interact with water and you'll get a flash, if what they said is happening is really happening in the sun. And guess what? They set it up, and they tested for it, and they were right. They were right. Just like it, just as many as predicted. About as many as predicted. They were a little off, but not far off. So they have detected neutrinos. Very cool equipment here. The Japanese have a couple of these. I think we've got one, or maybe we had one. Your book talks about it. You'll have to read about it. But they have shown that what they thought was happening inside the sun is actually happening, and so they can be correct about their theory. Isn't that interesting? Yeah.
Looks expensive.
I'll pass around some magnets. Let you play with it for a little bit. Try and turn the magnets around and make them hit each other. And pretend that you have two protons and you're trying to make them stick together. But they won't go together. Will they? Because they're oppositely charged. Push as hard as you can, try and make them touch. You can make them touch if you're strong enough. But imagine this, multiply this by 1,000,000, and that's the force needed to push two protons together. And it cannot, this force is hard to find a force that great. We can do it on Earth with our particle accelerators, but it can really be done well inside the sun with gravity. Gravity is that strong. It can pull these things together and make them touch even though they don't want to touch. Isn't that fun to play with? Rare earth magnets. That's what y'all need to get at home. These are. Okay? Isn't that great? All right, you can turn that off. We are